Find all real values of x such that f of x is equal to g of x. These are the intersection points, at least the values of x at intersection points. Our first function, we have a quadratic function, x squared plus 2x plus 1. And our second function is linear, 3x plus 7. When we set these functions equal to one another, there is a dominant quadratic term. And when I see that, I want to move all my terms to one side. Subtract 3x's from both sides, and then we're going to subtract a 7 from both sides. Really what we're after is getting it all on one side and equal to 0. 2x minus 3x, that's negative 1x. 1 minus 7 is negative 6. This is a trinomial quadratic equation, so it will factor, lucky for us, we don't have to use the quadratic formula, it'll factor as x plus 2 times x minus 3. Remember, you want the sum to be your middle value and the product to be your constant. And that's what we've got. X plus 2 is equal to 0 when x equals negative 2, and x minus 3 is equal to 0 when x equals 3. These are the x values at the intersection points. If you needed the actual coordinates, an easy way would be to take negative 2, plug it into 3x plus 7, and that would give you 3 times negative 2 plus 7 is 1. So it would actually give you the point negative 2, 1. Let me do better than that. Let me erase that. And then if we plug 3 in, 3 times 3 plus 7, that's 16. So these would actually be the coordinates of the intersection points. For this one, really, we were just going after the values of x. But that's how you would get the entire point if you needed to. Because it's the intersection of both functions, you can actually plug your x's into the simpler looking function. Find the difference quotient and simplify your answer. Let me zoom in a little bit. Here we go. We have a quadratic function of x squared minus 2x plus 7 given. The difference quotient we're asked to compute is f of 3 plus h minus f of 3 all over h. These difference quotients show up a lot in your Calculus 1 class, so that's why I cover them quite a bit in this class, just to make sure you're prepared. Upper left, let's calculate that, f of 3 plus h. You go back to your function, replace the variables with 3 plus h. That will give us 3 plus h squared minus 2 times 3 plus h plus 7. If you take two 3 plus h's, 3 plus h times another one, and FOIL and combine like terms, you will get 9 plus 6h plus h squared. Distributing negative 2 is negative 6 minus 2h plus 7. Combining all your like terms, we have h squared. 6h minus 2h is 4h. 9 minus 6 plus 7 is 10. And that is our upper left portion of the difference quotient. It's called difference quotient because you have subtraction or difference, quotient because of the fraction or ratio. The upper right part is not usually very hard to calculate. Most of the time it's simplify or placing a number into your function. So f of 3, that's 3 squared minus 2 times 3 plus 7, that's 10. Now we go under our difference quotient, replace the upper left with h squared plus 4h plus 10, minus f of 3, which was just 10. The 10s will cancel each other, h squared plus 4h all over h. Factor an h from your numerator, cancels the h from the denominator, leaving h plus 4. That is your simplified difference quotient for that function. Our second example, we have the function f of x equals 3x minus x squared. I'll get it out in a minute. The difference quotient we're asked to calculate is f of 3 plus h minus f of 3. over h. They're not always built that way. It's just how they were built in our homework set. Upper left, sub in 3 plus h for your variable. 3 times 3 plus h is 9 plus 3h minus 3 plus h quantity squared. Now we did that in the example above. Hold off on your subtraction until you get that squared. 3 plus h times 3 plus h is 9 plus 6h plus h squared. Exponent before subtract. Now we can subtract these three terms, basically distribute a negative 1. Combining like terms, we have a negative h squared. 3h minus 6h is negative 3h. The 9's zero each other out. So this upper left part of the difference quotient is negative h squared minus 3h. The upper right is f of 3. Substituting 3 into the function above, 3 times 3 minus 3 squared, 9 minus 9 is 0. So that upper right is 0. That simplifies to negative h squared minus 3h all over h. Factor out either an h or a negative h. That's your preference. In class, we factored out a negative h, so that left h plus 3 after factoring out a negative sign and an h. Cancel your h from top and bottom, and that leaves negative h plus 3. Switching gears, we have a problem where a graph is given. Use the graph of the function to find the domain and range of and find values. Okay, so we have a graph that begins at the point negative 1, 4. It decreases a while, then it increases, has a hilltop, and then the bottom falls out of it. The domain is the set of all x values that you can find somewhere on this graph. Since there are no x values less than negative 1, our domain begins at negative 1, and as you travel right, your x's get larger and larger. So its domain is negative 1 to infinity. The range is the set of all y values captured by your graph. Well, since it heads down forever, there is no lower limit on your y values, but as you work your way up, we approximated this in class to be about 7.3. Anything more than 7 and around 7.5 is okay. If you have to eyeball it, just make sure it's a pretty good attempt at eyeballing it. The y values captured by this graph are negative infinity to that peak at 7.3 approximately. There are some function values that you might be asked to find. For this first one, we're trying to come up with all values of x for which the function is 0. Well, that happens at 3. When x is 3, the function value is 0. Now notice on the next two, you have numbers given in parentheses instead of on the end. If the numbers are given in parentheses, that's your x coordinate and you're trying to find a y coordinate. Well, when x is negative 1, the y value paired with that is 4. And when x is 2, the y value paired with it is 7. So these are very quick. In the second graph, we have a parabola. It is opening downward, and that's okay. The parabolas, they like to go either up or down, hills or valleys. Those are associated with quadratic functions as well. This graph covers all x's, negatives, 0, positives. There are no x's that you can't find on the graph. This one has an unrestricted domain, negative infinity to positive infinity. Since the graph does open down, y's can get really negative. There's no lower limit to how negative they'll go for this particular graph, so your range starts with negative infinity. There is a largest y value. At the very top of the hill, the y value is 9. and it never goes higher. So that's where you cap off the range. The values of x where your function is equal to 0, there's two places. At -3, your function value is 0. Also at +3, your function value is 0. When x is -1 on the graph, you'll find your y-coordinate to be 8. When x is 2, you'll find your y-coordinate to be 5. A vertical line test is very simple. For any graph you have given, if it's possible to draw a vertical line through the graph and it strikes more than once, you do not have a graph that represents a function of x. 2 or more strikes with a vertical line, you do not have a function of x. Find the zeros of each function algebraically, verify graphically. Our first function is square root of 3x plus 2. Square root of 3x plus 2 is equal to 0. Square both sides. 3x plus 2 is equal to 0. Subtract 2, divide by 3. This function is equal to 0 if x is -2/3. Down here on the graph, we put a dot at approximately -2/3 and used our graphing calculator to get the graph of square root of 3x plus 2. That x-intercept occurs when x is -2/3. Our second function, f of x equals 3x squared plus 16x minus 12, this one's actually factorable, but we went ahead just for extra practice in class and calculated its zeros using quadratic formula. Set your function equal to 0, solve for x. X is equal to -16 plus or minus square root 16 squared minus 4 times 3 times -12. We have a -16 in the upper left, 6 in the denominator. The discriminant is a positive 400, and that tells us we're going to have two x-intercepts, two real solutions. Square root of 400 is exactly 20. Using your plus sign, -16 plus 20, that's 4 over 6 is 2/3. Using your minus sign for the other solution, -16 minus 20 is -36. Divided by 6 is -6. That tells us exactly where the graph of this function will cross the x-axis. At approximately 2/3, well, at 2/3, but we just had to approximate it with a dot, and at -6. Because the x squared term is positive, I know that the graph has to open up and go through those two specific locations.